Here we have two regular pentagons with the side of 2. There's also a segment AL. On that segment we have point K such that the angle EKG is 90 degrees. And we asked to find the distance from point C to point K. But before we're going to go and solve this problem, let's for a second forget about those black lines, red line. You just concentrate on the blue lines and the beauty and the symmetry of those two pentagons. First of all, let's talk about symmetries. There are several symmetries right here. One of them, probably one of the most obvious one, is the line ED. It's a line of symmetry. What we have on the left, what we have on the right are mirror images of each other. In a similar way, BG is a line of symmetry. What's above and what's below are mirror images of each other. And because of that, H will be in the middle of a segment ED, and the angle between ED and BG will be 90 degrees. The other interesting thing is point H. This is actually a point of symmetry. And the line AL goes through the point H. Now, what else can we find here? Now let's go back to our black and red lines. Notice we have two congruent angles here, angle EHG and angle EKG. It looks like this. And if we see a picture like this, we immediately need to think that all these 4 points are on the same circle. And the quadrilateral EHKG is an inscribed quadrilateral. So in this picture, this is our circle. But we can have this circle for any angle H and K as long as they're congruent to each other. But we have a specific angle of 90 degrees. So notice that EKG is an inscribed angle which is 90 degrees. And if we use inscribed angle theorem or Thales theorem, we'll find that EG has to be a diameter of our circle, and point O is the center of a circle. Now, if you're not familiar with inscribed angle theorem or Thales theorem, there's a link below. You can go and get more information. This means that EO, OG, OK, OH all have the same length. And now let's find that length. Notice that EO is a half of EG. EG is a diagonal of the regular pentagon. And we can find the length of this diagonal by applying a law of cosines to the triangle EFG. To do that, we need to know EF, we need to know FG, we know them, they're equal to 2, and we also need to know the angle F, angle between them. So first of all, let's find that angle. To find that angle, notice that we're dealing with polygons, and the sum of angles of polygons is 180 times n minus 2, where n is number of angles and the sides of a polygon. In our case, we're dealing with a pentagon that has 5 angles and 5 sides, so n equals to 5. And that means the sum of angles is 540 degrees. These are regular pentagons. It means that all the angles are of the same measure, all 5 angles. And that means that each angle is 108 degrees. Now, if you apply a law of cosines, we can find EG. We know EF, we know FG, and all we need is to find cosine of this angle of 108 degrees. 108 degrees is actually 90 degrees plus 18 degrees. And there's a well-known formula in trigonometry that gives us cosine of 90 degrees plus something. And that's actually equal to minus sine of that something. In this case, it's sine of 18 degrees. So if you find sine of 18 degrees, we can find cosine of 108 degrees, and we can find EG. Now, sine of 18 degrees is a standard angle, and I actually have two videos, one using trigonometry and one using geometry, where I derive the value for this angle. So I left links to those videos below. But what we need to know now is that sine of 18 degrees is square root of 5 minus 1 over 4. We can plug it in here, get cosine, plug it here, and calculate EG, which is equal to this. If you apply this formula, you'll find the expression on the left, but this expression equals the expression on the right. To make sure that it's the same thing, just square both sides and you get the same number. If you're interested how to actually get from here to here, I have a video when I actually do it, and the video is below. But for what we're trying to do now, it doesn't matter whether we use this formula or this formula. Either way is fine. Now notice that AE and EG seems to be two segments that lie on the same line. And this observation will be correct, but we need to show this. We need to prove it. To prove it, let's start with this angle, angle F. We know it's 108 degrees. We know that triangle EFG is an isosceles triangle. Angles at the base should be the same. So both of these angles will be 36 degrees. But then if you look at this angle DEF, this angle is also 108 degrees. The bottom part is 36 degrees. The top part has to be 72 degrees. But now if you look at this angle right here, AED, that angle is also 108 degrees. Now if you look at the angle AEG, we just need to add these two angles together and we get 180 degrees. And that proves the fact that AE and G are on the same line. All right, we're done with general observations. Let's just go and try to solve the problem. We want to find this segment CK. And to find this segment, we need some kind of triangle, quadrilateral, something. So we can create a triangle, ACK, and we can use the law of cosines, for example, to find CK if we know AC and AK and the angle between them, or more precisely, cosine of the angle between them. What we're going to do from now on is to use law of cosine multiple times to find many different things. Find angles, find sides. So by the time when we're done, you'll be an expert on the law of cosines if you're not now. So buckle up. We're going to have a bumpy ride. So what we need to find is AK. We need to find the angle right here. We do know AC already. AC is the diagonal of a pentagon. It equals to EG, and we already have it here. Now, how do we find this angle right here? Well, we know the angle right here, this big angle here. It's the same as this angle here. It's 72 degrees. And to find the angle right here, CAH, we need to take 72 degrees and subtract the angle right here, HAE. Now, what it means that we need to find this angle HAE. We can find cosine of this angle using law of cosines applied to the triangle AHE. The problem here is to do that, we really need to know the side AH, side EH, and side AE, all three of them. Right now we know only two of them. We know AE and we know EH, which is 1. But that's not a problem, because we can find the side AH using, again, law of cosine. In this case, we know AE, we know EH, and we know the angle between them, 180 degrees. And that's sufficient to find AH. And then we can use all the three sides to find cosine of this angle. So let's proceed. First of all, we need to find AH. So we can apply law of cosines in this way. We know AE, we know EH, and we know cosine of 180 degrees. It is minus sine of 18 degrees. That is written here. We can plug everything in and get our AH. Now we know AH, we know the other two sides, we know all three sides. So we can write law of cosines for this side, EH. Notice we know everything here except for cosine of angle HAE, this angle. So we can use this expression to find cosine. And that's what we're going to get if we do this. Now we know this angle. And what we're going to do, we're going to use this value for both finding the angle CAK and also for finding AK itself. So let's start with AK. Again, let's apply law of cosines to the triangle AKO. So we can express the side OK. In this case, we're going to get the cosine of angle A here. And now notice that we know here everything except for AK. We know OK, that's the radius. That's a half of EG. We also know AO, which is 2 plus the radius. We know cosine has been calculated. We don't know AK. And the AK comes here as AK squared and as AK. So this is essentially a quadratic equation for AK, which we can solve to find AK. When we solve it, we find two answers. The first answer, look at this. It's actually this guy. It gives us AH. And the second answer is our AK. Now you may be wondering why we found two answers. We asked for AK, but we found two, and one obviously not AK. It's AH. What's going on here? Well, what's going on here is actually the way we specify our triangle. We said that we want to find a triangle, or the side of a triangle, if we know two other sides, and the angle that is not between those two sides. Remember, there is triangle congruency criterion that essentially tells us that we can have a single triangle, a unique triangle, if we specify two sides and angle between them. But if angle is not between them, well, there's no criterion. And that's exactly why we don't have this criterion, because really both triangle AHO and triangle AKO satisfy the conditions we specify. One side is the radius, the other side AO, and we have this angle A, which is not between those two sides. If you're interested in more details on the subject, I have a video called the fourth triangle congruency criterion, and there's a link below you can go. So we found AK. Now we need to find this angle CAK, or more precisely cosine of this angle. Cosine of that angle is cosine of 72 degrees minus angle HAE. There is a formula for cosine of the difference of two angles. If you're not familiar with that formula, there is a link below. But for now, we just need to know the final result, that cosine of the difference is product of cosine of both angles plus product of sines of both angles. But notice for now, we only know cosine of angle HAE. We don't know anything else. So let's find them out. Let's start with cosine of 72 degrees. 72 degrees is 90 minus 18. Cosine of 90 minus something It's actually sine of that something. If you're not familiar with this formula, there's a link below. But that's something we already know. It's square root of 5 minus 1 over 4. Notice that previously we considered cosine of 108 degrees, and that was cosine of 90 plus 18 degrees. In that case, there was a minus in front of the sign. So we got the cosine. How about sine? Well, we should remember from trigonometry that there is a formula related cosine and sine, that cosine square of an angle plus sine square of the same angle is always 1. That's actually a consequence of Pythagorean theorem. So we can apply that formula to get sine, and that gives us this expression. We can find sine of angle HAE in a similar manner because we know cosine of that angle. And that gives us this complicated relationship. Now we're ready to plug all these values in, and if you do, you're going to find cosine of the angle we're interested in. And now we're almost done. We can apply law of cosines to find the CK. We know AC now, we know AK, we know cosine of the angle between them. If we apply everything, we find X. But now notice, this value is very familiar to us. We actually have seen it before. It's the length of the diagonal of a regular pentagon. So what it really means, that if I have a circle with a center at point C, and the circle goes through point A, the same circle will go through point E and through point K. So, if you can find an easy way to prove that fact, you may be able to find the length of CK in much easier way than we just did.